based on the title of my talk, I'm sure that you can imagine that while you were all watching Jose's talk with great fascination, I was watching it with great trepidation to figure out if I would actually have a talk at the end of things he had to say. But it turns out I do. And that's because this is stuff that we can do right now and that we actually are running in production. And it's but it's been a very active area of development and it's a lot of fun. So a big theme in the conference has been this. And that's because it really is part of that transition from just the simple request response. And we can do all kinds of things that we would not really envision doing and have them interact with that request response. And I've been told this might not actually be an apt analogy, but Bruce figured out that I was actually 8 when this happened, so you'll have to forgive me if I don't know the context with as much detail as some of you. But the basic idea is that in addition to the request response, we're dealing with data, and data is messy. We are pulling queues, we are sort of getting data in from financial systems, and external APIs that we have to deal with are not always the best. Some of them are very old, some of them are new, but just bad anyway. And there's all kinds of inconsistencies about whether or not you're going to get one of them. You often, because it is a request, you're going to get as many as it'll send, but it might be paginated and all that jazz, and you want it to get it to the right place. So the answer for that is, as it has always been, encapsulation. And specifically, I want to look at some particular mechanisms of encapsulation that Elixir gives us, and then look at how we can use those in the process architecture that OTP has blessed us with. So there's enumerable, which is about taking things out of stuff, a very generic thing, and then collectible, which is putting things into. Collectible won't really show up till later because we won't need it till later. But not only does enumerable and collectible give us encapsulation, it gives us really great composition in that there's this sort of well-defined manner for putting functionality together, and that functionality can be anything that from just like a file to an actual SQS queue, and you can stick that into a customer API. The data flow here is generic. This also really helps with testing, which has been a subject of a lot of discussion on the mailing list lately. And if you think of, if you take that queue, for example, in that customer API, and you wrap the stream itself in a function, so you're not really like hard coding that. In your tests, don't pass in a queue, pass in like a list of 3 maps that represents your test data, and then you can actually just assert on the results that are there. Streams are really, really great for all of that. But then, of course, as we saw this morning, when we get to the supervision story, what are we going to put there? There isn't anything that works at the moment. And so we're going to be looking at that. But before we do, I want to look at sort of the nature of what we're putting there, of what the cool stream is going to be first, because that's going to inform and sort of constrain what exactly we can use to run it. So first off, for those of you who are not super familiar with enumerable, this is the sort of pared down version of enumerable for file in the standard library. I left out all of the error checking because then it wouldn't fit on the slide. But the basic idea is that you have this top block where you can kind of open up the file in this case, and then you're just defining, there's a number of callbacks that you have to handle, and by and large, you don't actually have to do them yourself. There's some complexity there, but with things like stream resource and stream unfold and so on that are already in the standard library, you can just take your problem, define it as just a little next function, for example, which is just the IO stream from the file, and you just pass it to stream resource, and then you're done. So you don't really have to implement you don't have to understand all of the complexities that can exist there. This is great for a variety of reasons. For one thing, stream resource, as we'll see, actually, I'm not going to say that yet. I'm going to just move to our silly example that we're going to work with for the time being. So GitHub has an API that gives you events. And we're going to be streaming those events because you just really want to stay on top of what's going on in the Elixir world, for example. So this is what a GitHub, this is somewhat pseudocoded, but you can see what you might be doing here. What's neat about the sort of next function here, you'll notice it returns a tuple of the events that we've gotten and then the time. That time is going to act as kind of a paginator. We get all events up to some moment in time, and then the next request we do, it'll be, you know, return a new point in time that we'll get all the events after. The events can be one thing, it can be many things, and the enumerable API here, you can just enum take, you can just take however many you want. It'll still appear as though you've gotten them one at a time, but in the background, it'll fetch however many the GitHub API will let you do. So you're not having to do extra overhead just to get a nice kind of one at a time way of approaching or way of interacting with the stream. So here's what a stream that uses that might look like with some pseudocode. So we've got Elixir Lang and Jose Velim we're gonna stalk on GitHub events, and we're gonna throw it in Slack because that's just really what we want to do. So this really, if there's anyone have any questions about what this does so far, because if so, we're not going to make much more progress. All right, so now we're back to here. And when I was first trying to do this, our practical case was we wanted to have some kind of just task worker that was, or task scheduler that was getting things off a queue and then trying to just run the tasks. I was like, hey, the word task. That exists in the standard library. How about I just do this? You can pass task a function, and you can just give it a stream and call stream run, and then it'll just churn and do its thing. This is not a good idea. Despite the fact that it certainly looks like I could be done, it's not. It's not a good idea. Oh, that went away for some reason. Anyway, this is because that doesn't do any mailbox checking. You can't respond to any system debug messages. You can't get it's not a good OTP citizen. And so that will just grow indefinitely, which is generally undesired behavior in a process. And you also, when it's time for the supervisor to shut it down for whatever reason, it would be really cool if we could hook those exit messages into the halting ability that streams already have built in so that it could clean up any of the things that it had started appropriately. So what we ended up with was what's called StreamRunner, and that was built by James Fish, greatly indebted to him. And StreamRunner is great. It basically, and we're going to go through how it works in some detail, or in sort of a medium amount of detail, because it'll clarify why it is that we needed more than this. But basically, if that previous example we had, if you plug it in there and you call StreamRunner, it will simply iterate through the stream. And so what it does is when it begins in sort of the init block, it takes the stream and it suspends it. And there's some details here you don't really need to worry about, but the long and short of it is that what that continuation variable gives you, it's a function, it's an anonymous function, and you can call it with any of the enumerable messages isn't exactly the right term, but the sort of defined inputs that can continue a stream or halt a stream or whatever. And then in StreamRunner, there is a receive loop that does that. So the thing to know is that this is actually not derived from Gen server. It's derived from Gen, which makes it sort of a sibling of Gen server and Gen event and so on. And the thing that the Gen server module in Erlang does is that it has a loop, much like this. This is a very, 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 very simplified version. But it has a loop, and it loops over the inbox, and it can do things like here get a message from its supervisor that it should exit, and then it can terminate the stream. Or it can handle debug messages. And if it doesn't get either of those things, it just gets the next item on the stream and loops. And that is interesting. This was a really enlightening investigation for me, because I'd been using Gen servers for the last about as long as I've been using Elixir, but I never actually dug into hey, how does this work in terms of, and it's not as bad. There's a lot of logging stuff, but when you actually look at the core loop, it's very readable, and I highly recommend that you look into that yourself. The trouble here is that what if we had a situation where we wanted back pressure? So to pick my example, we don't want to run an arbitrary number of jobs. We just don't have that kind of resources. And this is a problem. Because if you look back to sort of, and you get rid of this is the core part of the loop. And it really is just like a recursive loop over the stream, and it will go as fast as it possibly can. And if you're enumerable, if you suddenly get, if we go with our GitHub newsfeed or our queue, if you suddenly get a huge number of items, you're going to start exactly that many tasks. And that's not really what we want. What we want is to let our consumers dictate the pace. And this is going to start sounding pretty familiar. What we want is a demand and supply pattern. But we're actually going to go into how I've implemented this in a variant on StreamRunner which I've termed StreamRouter, sort of, and sort of what it can do and what its limitations are. So as Jose covered in pretty good detail this morning, we would like the things that we're streaming data to be able to articulate exactly how much they can handle and have the stream only supply them that quantity. So it's going to need to be async, and this is a really important thing to note because it's actually somewhat at odds with the initial construction of enumerable. So back to it occurs to me. Back to the backpressure concept. So one option here is like, all right, we could just have the task scheduler just not reply until it can start something. It could just block. And that's not a very good thing to do. And that's for a couple reasons. One, it means that the process running the stream is now being blocked a lot, which makes it hard to respond to all the messages and is sort of exactly the same problem we invented StreamRunner to solve. It also means that you can no longer treat the gen server call timeouts can no longer fulfill the role that they're designed for. You're supposed to, there's a reason they're 5 seconds. You're supposed to, and then it exits if it doesn't work, is that most of the time it's supposed to be indicative of a problem, of some kind of issue that your system is locked up if you're not getting a response from your gen server. And with a task queue, it's really hard to say how long you should expect, and that expectation is going to vary over time. So we don't want to block. And so the demand is going to be totally asynchronous from the supply. You're going to ask for things, and then they're going to be sent to you in an asynchronous way. The other thing that that lets you do is we want to make sure that having the supply-demand relationship does not require that the sinks live or die along with the source. It would be great if one particular sink misbehaves, it's killed by its supervisor for some reason, that when it comes back and is reincarnated by the great gen server or by the great supervisor, it can reconnect and go back to doing what it's doing without taking down everything around it. The supply, on the other hand, we do want to be synchronous for exactly the same reasons we didn't want to block earlier. That we want the timeouts to serve their role. So let's take a look at the StreamRouter Loop. This is going to be pretty similar. I've left out the exit stuff and the system debug messages for the moment because they're exactly the same. The basic idea here, this is based on the Gen Router messaging protocol that Jose has been working on. But when the stream is started, it does the exact same thing that StreamRunner did, is that it suspends the stream. And so now we have this continuation function. We have sinks, which ends up just being a map of PIDs to demand integers that we're managing. And then we have aggregate demand. And aggregate demand is because in the current structure of this, the stream will only iterate as fast as the slowest demanding thing. And that's a sort of current limitation. It's part of limitation. It's partly a just design decision. But that's something that there's a number of items in here that are worth evaluating if we can extend them. And that's definitely one of them. Because at the moment, if there is no aggregate demand, it will simply wait until it gets a message because there's literally nothing else it's going to ever do. Otherwise, it will continue the stream. Now you'll notice it keeps track of the demand, it calls continue, but it doesn't actually get the value out of that. And you're probably wondering, that's weird, how on earth does the value end up to the subscribed processes? That too is at the moment a design decision. You'll see where that comes in a moment. Because the thing that I really like about the streams is that it gives you a really declarative, lets you write declarative code, declarative with respect to what your data flow is going to be. And so I use those same mechanisms to actually establish the when and the where of that of the message that's going to send the event that we get from the stream to the sinks. So a little bit more on the demand tracking. We also, when we get a stream, or when we get an ask message, we want to make sure we monitor that sink so that if it exits, we can remove its demand and safely handle that case. And that's that basically little detail. So the trouble is that the thing we had before is not going to work anymore, because if we're simply calling some API on your gen server, there's no way in this structure to connect the scheduler or the queue in this case to the StreamRunner and vice versa. They have no idea how to know about each other. So this is where Collectable comes in. So Collectable, I'm going to start off with just explaining the same file into, because that will, I think, clarify for people who aren't familiar with Collectable. Collectable is, has anyone not seen like the stream into some file thing? It's just exactly the same way of lazily taking an item and putting it into whatever you've implemented Collectable for. So in this case, for a file, you get this great little function up top, and this is where you get to, in this case, open a file. But this runs when the stream is suspended, and it runs only once. This turns out to be very handy. And then you define a series of functions that match on either a continuation or a done or a halt, and they can handle either adding an item or closing down any kind of resources you need. So with that, it actually is really easy to look at making a process collectible. So what I have is that when we stream into a particular a struct that's going to be associated with a module that is running a gen server, we can call add source on it. There's a number of callbacks that am sort of still working on exactly how I want to have that API, but I'm hoping that we can, just how you can use gen server to sort of deal with some of the boilerplate, you'd be able to use StreamRouter that would handle a little bit of the boilerplate of setting up these connections. But this would add the source so that and it's adding self, because this is running inside the StreamRouter process. And so it can send that PID to the subscribed process. And then we can, anytime we get a continuation message that we have an item, we can route that item to the process. And then the EOS is the end of stream. So if we're done or we're halted, either way, stream's all over. And so we're going to let our subscribers know of that. So this is what using this in, say, the task scheduler might look like. I've left out a little bit of the boilerplate, as you see, but with StreamRouter, we just have a handle call that's a stream item. Again, like that's something I'm still kind of working on. I've not yet decided if I want to have like a particular handle underscore something like handle event, but people who are better, who know more familiar with that, can tell me what's the best route. But in any case, you get an item, and then you can go start a task, and then presumably when a task is done, you'll get some kind of task done message, and then you can go ask the stream, which has been stored in your process state, for another item. So that gets us this. We can actually, we start a task scheduler in your supervision tree, and in this particular case, I'm using the PID, but you could also use a name, would be probably the easiest way, and then you pass in to the stream that module and the PID, and you can actually, stream into is great because you can give it this little function on the end that'll only be run for items going into it. stream into just passes along the value it was given. And so you can, in my particular case, I pass it back to the queue to be deleted. And then you can start that as a supervised thing as well. And it works. Like, this is an actual production code thing we have for coming from an Amazon SQS queue and running into a task scheduler. So that part works great. But, bonus question, what here is still blocking? Anybody? It's fine, it was rhetorical anyway. What's blocking is the queue itself. And this has to do with the nature of calling the enumerable continuation function, because when you are composing like stream.map, stream.filter, or whatever on top of any other stream, you don't really, it's usually build it from the top down, where you see like the file's up top and then you've got your map and your filter or whatever. But it's when you actually are trying to get an item out of it, you're saying to the bottom thing, hey, get me a thing. And then it says to the next layer in, hey, get me a thing, hey, get me a thing. And then it sends a thing back and maps all the composed functionality over it. But that is, by the very nature of enumerable, a sort of synchronous operation at the moment. And that is, that's kind of a big problem, because it means that suppose you're dealing with you know, something that you want to use long polling to, so that you can, you know, not do a zillion requests. Well, that 10 seconds that you're waiting for a long poll, the stream router is going to just be stuck waiting on it to get back. And you could try to make that particular part asynchronous, but even then, suppose you just don't have anything that shows up in your queue, or you're monitoring your GitHub newsfeed, and it's just everyone's at ElixirConf, no one's doing anything, and nothing's happening. There's just no item, that stream is not actually going to return anything, which means that the loop of the stream router or StreamRunner or anything that's trying to loop over that can't continue. So that really is one of the things that made us, that I think was a big factor in revisiting the question of, are we trying to make streams monitored, or are we trying to make monitored things stream? And if you start from that alternative view, we want to make that demand and supply thing asynchronous all the way through. And there's just an irreducible part of enumerable at the moment, at least as far as I can see, where that just isn't going to work. Unfortunately, by rephrasing the question like that, we lose some of the things that we already got to take for granted with streams, which is really easy semantics for linking processes together. Like, one of the things that I was thinking, and that it's just not a stage that we've figured out with GenRouter yet, is, you know, when we can start these things that are monitored, that part's easy. You stick a worker in your supervision tree. But then when we have like the genrouter.subscribe, where does that live? Like, and it has a sort of imperative feel, because if you're going to network these things together, you're going to be subscribing things, and that's manipulating state, because it's sending messages to processes and stuff. It would be really cool if we could have a declarative way for doing that. And I don't know what that is yet, but I do know that what's going to really inform what that looks like is using the kind of functionality we have right now that can do that kind of thing, because it's by trying to make that work that we've had so many of the sort of approach changes we've done so far. So I didn't finish my sentence on the last bullet there. Oh well. So where are we? So pipeline, we definitely want to avoid pipeline parallelism, and that's definitely something you don't want to do. But the thing that I think is also important to remember is that processes are more than just something you do because you want to make computation concurrent. You have all kinds of things, whether it's you're going to be buffering items until they hit some number and then you send them out in a batch, or you're managing a stateful task cluster, or there's all kinds of things where you have processes that need to be managing and maintaining their own state. And so streaming messages to them isn't really, you're not building a pipeline made of many processes because you just you're trying to do it in parallel and you don't understand how parallelism works. You can do that in such a way that lets you compose functionality you already have as an ordinary gen server for managing state with a stream of data that you can easily test and easily compose with other things. So there's still a lot of things that are yet to be nailed down with the StreamRouter. There was a lot of discussion that's really happened even in the last week about it. So it would be really cool, for example, one challenge with how we've written this is that you have to start the syncs, like the task scheduler or your the Slack notification thing prior to starting the stream, so that you can pass in that PID so that when the stream is suspended, it actually has somewhere to be like, hey, you're going to get data from me. It would be really neat if we could turn that around, because it often makes sense to establish the entity from which you are streaming data first and then dynamically add subscribers. It would be totally doable to dynamically add subscribers, but at the same time, it would be nice to keep the streaming into semantics, because that lets you, in a sort of glance, get a nice declarative overview of what your sort of code pathways are and your data pathways. And probably just wishful thinking. It would be neat if enumerable could be less blocking. That's probably not going to happen. I think there's something that is in the nature there. And that's OK. The good news is that what makes enumerable and collectible really great abstractions is that you could take whatever code it is that is in the reduce block or in the into function. It's by and large just your API calls and your parsing logic. That's where you're supposed to be putting out those calls. And if we come up with a better abstraction for doing non-blocking streaming, you would just move that over there. Like enumerable and collectible are so appealing precisely because they've understood how to get what the important part of establishing that relationship is. So that's all I have. And are there any questions? Okay, great.